Hello class, this is CSE-5250, Section 60, Week 2, Spring 2025. Alright, so a rather light, this is a rather light video. I might have to tack on an extra video explaining what we're going to be doing for our first programming assignment. So there might be an extra video this Monday, so just watch out for that. For now, before we even get to any programming, let's talk about why parallel programming. Why are we doing parallel programming in the first place? So, this is chapter 1, and it's basically why parallel programming. Why do we care about parallel programming? Computer technology is advancing, so can we just wait for a more powerful computer to hit the market? And also, if we have these parallel systems and we want our old programs to run on them, is there a way we can write a program that would automatically parallelize our programs? So, here's a little bit of backstory. Up until the 2000s, there was this observation that was made by a so-called Gordon Moore that basically posited that every 18 to 24 months, CPU performance would double. And up until that point, that observation held true, and we call this Moore's Law. So if you wanted a more powerful computer, all we had to do was wait for a more powerful computer to hit the market. The problem is, ever since the early 2000s, that trend has ended. So we don't have yearly performance gains of 50% anymore. They're more like 4%. And by 2005, CPU manufacturers realized that they can't get our computers any faster, so they started to add more CPU cores instead. And the core counts only went from there, starting with 2-core CPUs and then 4-core CPUs. And nowadays, it's not uncommon to see 6, 8, 12, 16-core CPUs, and even higher than that. Though once you get beyond 8, those are rather pricey systems. But my point is, we have CPUs with multiple cores, and even way higher than it was 10 years ago. For context, my first computer build was an AMD FX 4170 4-core 8-thread system on a rather poor architecture. This was back when AMD wasn't the performance king right now. And now, 10 years later, we have the flagship AMD Ryzen 9 99, whatever it is, and it's a 16-core 32-thread behemoth of a CPU. And that thing is only several $100s. Back then, that kind of core count would be unheard of. Even an 8-core would be prohibitively expensive. But by 2017, you could get an 8-core 16-thread CPU from AMD for just a little over $300. Can you tell I'm an early adopter of the Ryzen series? Anyway, really the main reason I went with AMD over Intel is because I somehow found I found AMD's lineup to be easier to understand over Intel's, even though it really is a clone of Intel's numbering system. But anyway, really interesting history between AMD and Intel. They would flip-flop between one another for best CPU on the market, and looks like it's AMD's turn to be on top again. There are various applications for which we want parallel programming, such as, but definitely not limited to, climate modeling. We want to be able to simulate as many air particles in a model as possible. We cannot hope to get a fast enough single-core CPU, so we would want multiple CPUs to divide the work and hopefully get a better climate model that way. Protein folding, and related to that, drug discovery. Particularly in the early days of the pandemic. People were just bored at home on their computers. They heard about a program called Folding at Home, which you may have known about as well. This is a program that when you download it, it connects your computer to a distributed network of computers, and they are all working together for protein folding. When people heard word about Folding at Home doing protein folding research on the coronavirus, so many people downloaded Folding at Home that at one point the Folding at Home distributed system became the most powerful supercomputer in the world. Other applications include energy research and probably more relevant now, data analysis. I would probably add AI to that because to train a neural network, for example, neural networks are only just a small part of AI, but roll with me here. Neural network is at the heart of it a lot of matrix multiplication. It's one of those operations that when you have really big matrices, you are going to want to parallelize it so that you get your calculations being done faster. So let's talk about clock speed. As I mentioned, there was Moore's law that said that clock speed would double every 18 to 24 months. The problem with that is clock speed stopped increasing. Oh, excuse me. So as I was saying, clock speed would increase almost regularly up to the early 2000s, and then it would just plateau. We would not be able to advance beyond like 1 or 2 or 3 gigahertz for a while. And yet there are some records out there where for the longest time the clock speed record was around 8 gigahertz on an AMD CPU. That was recently beaten by a Intel CPU that managed to reach 9 gigahertz. So how come we don't see CPUs with that high of a clock speed? Well, it's simple. The more you overclock these CPUs, the more heat they output. And it's exponential too. So a little bit of a clock speed increase results in a huge amount of extra heat being output. So the point is this. We can get our CPUs faster, but to keep them cool requires cooling solutions that are generally out of reach from most consumers. Air cooling is, the cheapest and easiest way to cool down a CPU, but once you get to higher and higher clock speeds via overclocking, then air cooling starts to become insufficient. Yeah, there are liquid-cooled systems, but even that's not enough for these overclocking records. And they are records because no one is overclocking their CPUs to like 9 gigahertz. The highest we can go so far, the highest clock speeds AMD and Intel have been able to get to is 5 gigahertz now. There was even an entire controversy when Intel would showcase this 5 gigahertz CPU with like 20-something CPU cores. And hey, this Intel CPU can outperform AMD's best of the best. But here's what makes it so controversial. That CPU was overclocked and then cooled using a 1 horsepower cooling system. So yeah. This was several years ago, so my point is, if we want our CPUs to run faster by increasing their clock speed, at some point, keeping them cool becomes infeasible. And even if you did keep them cool, there is also the fact that, well, you need more power to keep them running. So, there is a power concern, as even more so if this is supposed to be a mobile device. So, even though over the years, transistors on a CPU shrank and shrank, back when I had that AMD FX4170, that was like, that CPU's transistors were like 32 nanometers. And now we have CPUs that are 14 nanometers and smaller. I believe on AMD's CPUs, they're like 7 nanometers, if not smaller than that. Don't quote me on that, but do your research if you want some exact numbers. My point is, clock speed has basically plateaued because the heat output on these circuits just became too high to manage. So, to make sure that our computers did not literally melt down, we more or less limited the clock speed on our computers. So that's why if you were going to buy Moore's Law by clock speed, Moore's Law should have been dead 20 years ago. Even if we can shrink down a CPU, and the main reason for shrinking the transistors on a CPU is we can get more processing power for the same amount of energy because everything's so smaller, so we don't need to use as much energy to run these things. Alternatively, we can use the same power to get more processing power. So we can get more CPU performance that way. But eventually we're going to reach a limit to how small we can make our CPUs, and at that point, we're going to have to do something else, and that's probably going to be more parallel programming. Well, actually no, parallel systems for which you have to do parallel programming. So in general, if we increase a CPU's clock speed, that increases its power consumption. This also increases the amount of heat being put out, and at some point, air-based cooling is going to reach a limit, and you're probably going to need some exotic cooling solution that is out of the reach of most consumers. What kind of cooling solutions am I talking about? Well, I mentioned that the record for clock speed is like, it used to be 8 gigahertz and now it's 9 gigahertz. On those kinds of CPUs, these insane clock speeds were only achieved not through liquid hydrogen, but liquid helium. So yeah, basically you need to slap an entire refrigerator onto your CPU. Not unlike the kind of refrigerator that would be used on an MRI machine's magnets, because those are magnets that have to be kept super cool. My point is, even if we could increase clock speed, to keep them cool would just be too infeasible for the average consumer. So that doesn't stop some computer enthusiasts from building their own liquid-cooled setups. For context, it used to be that clock speed was the only metric that was used to indicate that a computer was fast. I may have mentioned earlier that clock speed just recently reached 5 gigahertz on the fastest CPUs, when it was only around 2 to 4 for the past 20 years. Not including server or workstation CPUs, the highest core counts available are like at least 16 cores right now. Intel has a special i9 where there are more cores than that. They are like performance and efficiency cores, or so I'm told. Also, clock speed is no longer the only metric. IPC is also another metric, and other advances such as pipelining basically means clock speed as a metric for performance is, well, a bit incomplete. So why do we need to write parallel programs? Most programs were, up until we had parallel programs, all of our computers were single core systems. Therefore, our programs could only ever use one core. And sure, you can run multiple instances of the same program, but that isn't the same thing as having a multi-core system. If you have, say, 2 instances of PowerPoint, that doesn't really help apart from being able to work on 2 PowerPoint slides at the same time. There are a few ways we can get our single-threaded programs to run on multiple CPU cores. We can convert existing programs with a special program that can parallelize code, or we can rewrite the whole dang thing ourselves. As it turns out, researchers have found very little success in writing such converter programs, even in cases where certain operations can be parallelized. The resulting code may be slower, so at worst, we must redesign the code itself. So how do we write parallel programs? So there are 2 ways to do this. The first way is task parallelism, where we assign different tasks concurrently to different CPU cores, and the other one is data parallelism, where the same task is concurrently executed on different CPU cores. Think about it like this. Say we had a dataset that consisted of like 1 million data points. We need to perform some operation on each one, but it is the same operations. Oh, let's say it's a data point and we want to find, say... Okay, so let's say, for example, we wanted to find the weight of several... Excuse me. Say for each data point in that data set, it was several temperature values, and we wanted to find the average of each set. And there are like a million sets of these temperature values. We could just calculate each data point one by one, or if we have 2 CPUs, we could ideally cut this data set of 1 million data points in half, give 500,000 data points to one CPU, give the other 500,000 to the other CPU, with the hope that if both CPUs are running at the same pace, we achieve the same amount of work in half the time. And when we talk about, and oftentimes when we talk about performance gains using parallelization, this is the kind of performance gains we're talking about. Doing more work in less time. Data parallelism is a little bit... Okay, so what I was talking about was data parallelism. We run the same task concurrently on different CPU cores. Task parallelism is a little bit different. You like to talk about the example of... Well, there's several examples I could talk about, but let's go with a simple one. Say you have a word processor. You have a multi-threaded word processor. One thread is listening for keyboard input. The second thread is updating contents on the screen, and the third thread is saving your document periodically. So if you press the letter A on your keyboard, one thread is going to listen to that input, and then another thread is going to update to the screen. If this was a single threaded word processor, and let's say the program decided, hey, I need to save this document now. If you press A, nothing might update on the screen until the word processor has finished saving. Another example could be, say, a video game where you have several threads, one for the physics engine, one for the sound engine, one for listening to player input, and one for listening to your networks. Oh, this could be an MMO, for example. Did you get headshot between when you last clicked and now? So yeah, that is task parallelism. And yeah, I do have a lot more analogies on parallelism. One that's probably more closer to home is the task of doing laundry. Let's say you had a lot of laundry to do one day, and you only, of course, have one washer and dryer. Of course, in theory, you can just do one load at a time. Wash one load, wait for that to finish, put that first load in the dryer, and wait for that to dry, and then start folding that. Only after that would you start the next load. So, even though we have only one washer and dryer, there is a way of getting more work done faster. And this is how. You fill your washing machine with as much laundry as it can handle, and you start washing that load. You wait for that load to finish, and take everything out into the dryer, and then start that immediately. Start drying immediately. At the same time that is drying, you start another load in the washing machine. Once the dryer is finished, you take that out, set that aside, take all the wet laundry from the second load, put that in the dryer, and then start a third load of laundry to wash. And while the third load is washing and the second load is drying, you start folding the first load. This is called pipelining. Or this is the principle behind pipelining. So here we have a 3-step pipeline where 3 loads of laundry are in different stages. Yeah, up to 3 loads of laundry are being processed, but they're at different stages in this pipeline. Wash, dry, and fold. So that is pipelining. If you want real parallelism, another solution to this laundry problem would just be give up and go to the laundromat. So once you're at the laundromat, you can, for example, pick out, say, 5 laundry machines in which you can put all your laundry in. Though you will need to do some load balancing to make sure each laundry machine has roughly the same amount of laundry, but also to make sure that the load is physically balanced inside, because, well, you don't want the washing machines to shake and shake away from the wall. But my point is, instead of having up to 3 loads of laundry at different stages in this washing pipeline, we can now have up to 5 loads all washing at once. And when those 5 loads of laundry are washed, we put them into 5 separate dryers, and now we have all 5 loads drying at the same time. Of course, there's only just one of you, so you can only move 1 load at a time. But the point is, we are, apart from the work of moving loads around, doing the work of 5 washing machines in the time it takes for 1 washing machine to work. 5 times the work in the same amount of time. There is one little hiccup to this solution, and that is the fact there's only one of you and you have to fold 5 loads of laundry. Unless you have 4 other helpers out to help you out. The textbook has its own example, and here you do have helpers. Suppose you're a professor teaching a size 100 class and you have 4 TAs helping you out. The task now is to grade 100 exams. The exam consists of 5 questions. How does this professor and the 4 TAs grade all 100 exams? Well, there is an obvious solution. Divide those 100 exams into 5 stacks of 20. The professor and the 4 TAs each get 1 stack of 20. And they just grade away. The idea behind that is we are grading, on average, 5 exams in the time it takes to grade 1 exam. And that is the data parallelism solution to this problem of I need to grade all these exams. Another solution is task parallelism. Say the professor grades question 1. and the 4 TAs each grade questions 2, 3, 4, and 5 respectively. So they need to be sitting at some table, and the professor grades the first question, hands an exam to the first TA. The professor starts grading the next exam, while at the same time the first TA grades the second question, and then pass it on. And then the second TA grades the third question. At the same time, the first two graders are grading the first and second question, pass it on, and so on and so forth. In this task parallelism example, each person will have graded 100 questions each, but they will have each graded a different question. In the data parallelism solution, each grader will have graded 100 questions, but they'll have seen all 5 questions on the exam. So in effect, they will have graded the entire exam, but only 20 times. Same number of questions being graded, but they will have graded every question. That's the data parallelism solution. The task parallelism solution is they'll have graded one instance of the same question 100 times. There are a few things to consider. In solution 1, each test will have to be sent to 5 different graders. Another thing to consider is load balancing. Assuming all 5 graders can grade at the same speed, you need to give everyone the same amount of work. That's pretty reasonable, but sometimes it might be the case that one person in this chain might be grading a question faster than the others, and whoever's next in this chain might get a pileup of exams to grade. I'm talking about the task parallelism example. So what if the professor is grading the first question slightly faster than the 4 TAs can grade all the other questions? So I'm grading the first question, next, grading the first question, next, grading the first question, next, and wait, stop! I can't keep up! That's a synchronization problem right there. Even with load balancing, this could become a problem. So what we'll be doing is it says we're going to be trying 4 different APIs, but we're going to really focus on 3 of them. And the order is wrong. We're going to look at pthreads. It's called POSIX threads, but pthreads is short for POSIX threads. Pthreads, OpenMP, and then MPI. And these APIs can be classified in 2 ways. How they share memory, that be shared or distributed, and the number of independent data streams that they can handle. So in this classification, we can classify programs by whether they have shared or distributed memory, or whether they are handling one data stream or multiple data streams. So single instruction, single data, SISD, that is where we have one instruction stream, one data stream, basically your standard sequential program. In this class, we call this boring. Single instruction, multiple data, that is data parallelism. One instruction stream working with multiple pieces of data at once. Multiple instruction, single data, that is multiple programs working on the same data. The example given here is, say, a backtracking algorithm. Say you have a maze, and you have a bot with the magical ability to make copies of itself. Maybe it's a software bot traversing a virtual maze. Not a physical bot, say, like with Micromask. But anyway, we have a bot that can traverse a maze, and every time it encounters a fork in the road, it makes copies of itself. We say it forks. So, this bot finds a fork in the road. There are 3 paths that it can go onto. It forks itself into 3 bots total, and each bot goes its own way. And say one bot is going down one path, and oops, that path had terminated already. So it can backtrack, but if it were to keep going, but it can't keep going because there are 2 other bots already exploring the maze, and those bots may have already forked into more bots, each exploring a different part of the maze, and possibly finding dead ends as well. So, this is what's meant by backtracking. So, even if we'd probably have to backtrack all the way to the beginning because this system is already splitting itself into multiple bots. But what if there's a limit to how many bots it could produce? So at some point, there's... Okay, so let's pretend that this is a bot that can release smaller bots. If one of these smaller bots encounters a fork in the road, but all the other bots have already been dispatched, it would probably have to wait there for a bot that has backtracked to catch up to it, and then the 2 bots can split off and explore more of the maze. So yeah, that is multiple instructions, single data. I hope I did it justice with what this is talking about. The last one is multiple instruction, multiple data. Different instruction streams working with different data each. This is the most generalized model of all. So these would just be different processes communicating with one another, each with different data, and each process is doing something else. Single program, multiple data is a 5th classification. This is copies of a single program. And this program is allowed to execute different parts of its code on different data. This is task parallelism. So, we're going to be more concerned with this column here. SIMD and SPMD. So, SIMD is same instructions on different data. That is something called loop parallelization. So that's an interesting thing we can do. Loop parallelization is where we have a for loop, say a for loop where with like a million for loop iterations. This can only be done on certain types of for loops. We'll talk about that when we start looking. Yeah, we'll talk about that a little bit later. But my point is, if this is the kind of for loop where the result of the previous loop does not affect the result of the next for loop iteration, then we can, in a way, unfold this for loop into 1 million copies of the same code, and then just divide that work between 2 CPU cores. 2 or more, I should say. So, that's chapter 1, but I do have another set of slides that I have to bring up as well. So, this is the wrong one. Let me just put it on the right monitor. Swap. There we go. So, this is just a review of architecture. You're probably familiar with the von Neumann architecture. This is an architecture that consists of the main memory, a CPU, and an interconnect between the 2 things. An interconnect between the memory and the CPU. This is typically in the form of something called a bus. A bus is just a data path. The CPU can be divided into a control unit that's responsible for deciding which instruction to execute, and a data path that's responsible for executing the instructions. Within the CPU are registers. These store data and information about the state of an executing program. So how fast data can move between the CPU and memory depends on how fast that interconnect is. So a classic problem with the CPU and memory is the fact that if the CPU tries to access something from memory, it's going to take several clock cycles. By that I mean, in the time it takes the CPU to access something from memory, it could have been executing like several instructions. One by one, of course. And when people say memory is slower than the CPU, this is why. The CPU typically works at a clock speed that, depending on the system, may vary from like 2,000 megahertz, which is 2 gigahertz, to like 4,000 megahertz. So, in comparison to memory, it could be as low as 2,000 megahertz. So yeah, the CPU is generally operating faster than main memory. So if the memory is if the speed at which we read from memory is a bottleneck, can we do something about that? And the answer is yes. The solution is something called caching. We put a memory chip in between the CPU and main memory that is faster than main memory, but not as fast as the CPU. And because of the cost of this cache, we generally don't have much of it compared to main memory. But the point is, if we need to access something from main memory, if we have to access it for the first time, say we need to read something from address 1000, there's a good chance we're going to be accessing, if we're reading something from address 1000, there's a good chance we're going to need something from address 1001, 1002, 1003, 1004, 1005, and so on. We'll just get the whole block of like the next 100 places in memory, copy all of that into cache. So, if the CPU needs to read something from memory again, it checks the cache first. So if we get what we're looking for in the cache, that is called a cache hit, and that is good. So the idea behind what makes caching work is the idea of locality. And I guess another detail that will probably come up in, say, CSE-5250-60. Caching works because there is a predictable pattern to which the CPU accesses stuff in memory. Because if it were truly random, then caching would not work at all. CPUs these days generally have 3 levels of cache, appropriately called level 1, 2, and 3. So we have 3 levels of cache. If it's not in the level 1 cache, then hopefully it's in the level 2 cache. If it's not in the level 2 cache, then hopefully it's in the level 3 cache. Obviously, it's slower and slower and slower each time, but the hope is that it's in one of these caches, because if it's not in any of those 3 levels of cache, then we've got 3 cache misses in a row, then we have to go all the way to main memory and get our data from there. And once again, to read from main memory is slow. There's another modification to the von Neumann model called multiple issue. Multiple issue processors replicate functional units and try to simultaneously execute different instructions in a program. So consider this for loop. A for loop that adds 2 vectors. So we have a vector represented by an array called x and another. So we have 2 vectors represented by an array x and y. We are adding these 2 vectors and storing it in a third vector, z. So we are doing vector addition. So x1 plus x2, we store that value in x3. But this is also an x0, y0 equals z0. Or I should say z0 equals x1 plus y1. So we could have 2 CPU cores where one CPU core adds all the even numbered elements and the other adds all the odd numbered elements. So one CPU is adding z0, one CPU is calculating z0, z2, z4, z6, and so on. And the other CPU is calculating z1, z3, z5, and so on. This is called multiple issue. And this is where we can see a glimpse into how we can parallelize a for loop. The key is to find instructions that can be simultaneously executed. So multiple issue isn't just for special for loops like this, but it's also suitable for stuff like this. However, there's a problem. If we have an if statement that says if such and such condition is met, in this case z is greater than 0, then we say we assign w the value of x. Otherwise, we assign w the value of y. So if such and such condition, do this code. Otherwise, do this code instead. If we have multiple issue, what we're doing is we need to make a choice between which path to take. Or in this case, we could just do both. If z is greater than 0, we don't make that choice. We just do both blocks of code at once. So one of them is going to be the right answer. And once we have evaluated z is greater than 0, we just pick out the right answer and discard the wrong answer. Speculation is where the compiler or processor makes a guess about an instruction and then executes the instruction based off that guess. So, not so much doing both options at once, just picking one and hope it's the right answer. So speculation must contend with the possibility that whatever we picked may have been the wrong choice. So, if such and such condition, do this code, otherwise do some other code, we go with the condition that assumes the condition was true. Oh wait! That condition was actually false, so it should have been the other code that we should have done. So we have to throw out our result, backtrack, and do it again with the right block of code. So, we did w equals x when it should have been w equals y. We have to throw out what we did with w equals x and do w equals y instead. Hardware multithreading. So, instruction level parallelism may be hard to exploit, especially if there is a long sequence of what are called dependent statements. Here's a good example. The Fibonacci numbers are a good example of this dependence. So, if we have the starting values 1 and 1, I add those together to get the number 2. If I want to that is the next Fibonacci number after 1 and 1. If you want to calculate the next Fibonacci number after that, I have to add the previous 2 Fibonacci numbers that came before it. In this case, this was 1 and 2. I add those together to get 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13, and so on and so forth. This means if I want to calculate the 21st Fibonacci number, I actually need to calculate the first 20 Fibonacci numbers before that. Well, technically there is a way to skip that, but if we're gonna go by code that looks like this, we cannot calculate the 21st Fibonacci number without first calculating the first 20. This also means there are certain types of for loops that cannot be parallelized. Once again, there is a way to calculate the 21st Fibonacci number without doing recursive calculations, but my point is, this is to demonstrate dependent statements, where the result of one for loop iteration contributes to the result of the next for loop iteration. There's also more to hardware multithreading. A thread level parallelism attempts to provide parallelism through the simultaneous execution of different threads. This could be coarse-grained or fine-grained. Simultaneous multithreading is something that you may have heard already, and it goes by several names, such as hyperthreading. This is a variation of fine-grained multithreading, where one CPU is kind of like 2 CPUs. So, one CPU is holding the state of 2 threads, and it just alternates between executing the 2 threads. So, if, for example, we are to open Task Manager and look at my computer, for example, that's my 4080 Super. I actually want this one. This is an 8-core CPU, but notice how there are 16 line graphs here. That's because those are the threads that are spoken of when marketing talks about this being an 8-core 16-thread CPU. So it's kind of like there are 16 CPUs here, or logical processors as Windows likes to call them. So this is simultaneous multi-threading. This is how we can get more performance out of a single CPU core. And on Intel CPUs, this is called hyper-threading. Put it back. There we go. So remember this diagram from earlier? This is called Flynn's taxonomy. So Flynn's taxonomy is a way of classifying parallel hardware into one of these 4 or like 5 categories. We're going to be looking more towards the right column as you mentioned. SIMD and MIMD, and of course SPMD as well. So SIMD systems are parallel systems. An instruction, so here we have an instruction that is broadcast from the control unit to individual data paths, and then each data path either applies the current instruction to the current data or it's idle. So if we have, say, 1000 CPU cores, and they're all calculating this. So let's say this is a 1000 for loop. This is a for loop with 1000 loop iterations. We give one of those 1000 iterations to one of 1000 CPU cores. And then a control unit says, "Hey, execute this code!" And then all 1000 cores execute that code. There might be other cores that are supposed to be doing something, but they don't have anything to work on. Typically, when we're working with things like this, the quantities are typically powers of 2 or a multiple of a power of 2. So there could be, for example, 24 extra CPU cores doing nothing. But by having one control unit broadcast to all 1000 CPU cores, "Hey, execute this code," what we've done is basically done 1000 calculations in the time it takes to do one calculation. In an SIMD system, the data paths must operate synchronously, so each data path must wait for the next instruction to be broadcast before proceeding. So imagine there were extra steps to this line of code, to this for loop here. My point is, each core cannot proceed on its own. They must proceed all together. Furthermore, data paths have no instruction storage, so a data path cannot delay executing just by storing it for later execution. So what we've seen here, this is called data parallelism. So SIMD systems are ideal for parallelizing simple for loops that operate on large arrays of data. We're parallelizing a for loop here. There's also another piece of hardware called a GPU. What's a GPU do? So a GPU is a multi-core processor for displaying graphics on your screen. Graphics APIs typically use points, lines, and triangles to represent the surface of an object internally. And then a graphics processing pipeline converts that representation into something that can be displayed on a screen. Processing a single image can require a very large amount of data, like on the order of megabytes. Therefore, GPUs must maintain very high rates of data movement. To avoid stalls, the GPUs... Yeah, I miswrote that one. So yeah. So my point is, GPUs are an example of parallel processing because we want to draw stuff on the screen very, very fast. GPUs are not purely SIMD. They can be a mix of that and MIMD. Current generation GPUs can run more than one instruction stream on a single core. GPUs have dozens of cores, and each one can execute an independent instruction stream. And GPUs can either use shared memory, distributed memory, or, for the larger systems, both. MIMD systems support multiple simultaneous instruction streams operating on multiple data streams. Each processor operates at its own pace. They're all asynchronous. And there is no global clock. So instead of one control unit saying, hey, execute this instruction! And then, stop now and don't execute until I tell you to. We don't have a control unit here because every processor operates at its own pace. So how do we synchronize these things? Well, sometimes there are forms of synchronization that can be imposed depending on the nature of the program itself. But at any given point in time, MIMD processors may be executing different statements. And again, all at their own pace. Imagine, for example, you handed out the same Lego set to like 20 people, and the task was to just build out the Lego set. Without any synchronization, at any given time, someone could, for example, have the whole completed train already, or someone could, for example, be still stuck on building out the wheels. MIMD systems use either shared memory or distributed memory. In a shared memory system, every CPU shares the same memory via an interconnect. In a distributed system, each CPU has its own private memory, and each CPU communicates with all the other CPUs using messages over an interconnect. So, in terms of hardware, we have plenty of devices and machines that have multiple processors. In terms of software, it's complicated. Many programs out there can leverage multiple CPU cores. Microsoft Excel, Adobe Photoshop, Google Chrome are some good examples. I could also include Blender because when it comes to rendering stuff on Blender, you can divide that work between multiple CPU cores. Though there's also the GPU option for rendering stuff in Blender as well. But even though we do have all these multi-threaded CPU, even though we have multiple core CPUs and software that can leverage those multiple CPU cores, we still have many programs that are still using one single thread. We can't get any more performance increases through hardware alone, so we must turn to programming for these performance increases. So here is SPMD, a single executable program that can behave as though it were multiple programs. And here's how it's done. If this is thread 0, do this code. Else, do some other code. We can make this a little bit more elaborate. So for example, if this is thread 0, do this code. Otherwise, if this is thread 1, do this code instead. Otherwise, if this is thread 2, do this code instead. And so on. We use an if statement for this. So a thread with a specific ID will do some task based on this condition being true or not. Sometimes we can get parallel performance so easily it's embarrassingly parallel. So this add operation here can be parallelized by dividing the work as evenly as possible. If there are, for example, like 1,000 elements and 4 threads, one thread gets 250 elements to add. The next thread gets the next 250 elements, and then the next thread gets the next 250 elements, and so on. As I said, embarrassingly parallel. So the steps are as shown. Step 1, divide the work so that each thread gets roughly the same amount of work. This is load balancing, and also to minimize the amount of communication required. Step 1. Step 2 and Step 3 are often interrelated. Arrange for the threads to be synchronized, and then arrange for communication among the threads. There are a few things to consider here, and a lot of this is basically a review from CSE-5250. If you have multiple threads or processes trying to access the same shared resource, you have the potential for a race condition. Or, as it's sometimes called, a race hazard. A race hazard is where you have 2 or more processes racing one another to do something with a shared resource. So imagine three processes trying to write something to the same slot in memory. So each of these three processes are trying to write a number, say 1, 2, and 3. The first process writes 1, the second process writes 2, and the third process writes 3. Which value sticks? Whoever has written their value last in a race condition, last place wins. To avoid race conditions, what we want to do with these resources is make sure only one process or thread can access it at a time. This is called mutual exclusion. We identify what is called a critical section, and then, as a programmer, enforce mutual exclusion. This is done through several ways that you probably remember from operating systems, but my point is this. We want one thread at a time to use a shared resource. Oh yeah. The steps of how to execute a critical section are as follows. Step 1. See if anyone else is using a resource, and if so, go to sleep. Once you're awakened by some other process that says, hey, I'm done with this resource, it's your turn, execute a lock function that says, okay, I am now using this critical resource. Then enter the critical resource, and then exit the critical resource and unlock the thing. Oftentimes this is talked about as acquiring a lock and then releasing a lock. Oh yeah, and Amdahl's law. This is a formula for calculating potential performance gains from adding additional cores to a program that has non-parallel and parallel sections of code. So this is something that I oftentimes like to demonstrate visually. So maybe I can get a pen, and let's just say we have some program whose runtime is, say, half serial and half parallel. So 50% of the runtime is done executing serial code, and the other half of the runtime is done executing parallel code. So the idea is this. And I hope you can see this just fine on your screen. If 50% of the time is spent executing serial code, and the other 50% of the time is done executing parallel code on one CPU core, if we have a second CPU core, what will happen is this. One CPU core will be executing the serial code. Yeah, so one CPU core. Let me back up. So what will happen is this. Once we get to the parallel section of code, the work being done is now divided between two CPU cores. So now we have done the parallel work in half the time. For this simple example, where we have half the work being serial code, half the work being executing serial code, and half the time this program is executing serial code. The other half of the time, the program is executing parallel code. And this is on one CPU core. If we have two CPU cores, well, it's still going to be one CPU core executing serial code, but once we get to the parallel code, we can divide the work between the two CPU cores, and now we're able to do the parallel code in half the time. So with two CPU cores in this simple example here, we're able to do the work in 3/4 the time. In an extreme case where most of a computer program's runtime is done executing serial code, then something like this. If most of a computer's program's runtime is spent executing parallel code, no, serial code, then even if we throw as many CPU cores at this problem, it's gonna affect only a small portion of that computer program's runtime. But if it were the reverse, say there's only a little bit of serial code and a lot of parallel code. So if the majority of a program's runtime is done executing parallel code, then we can increase the amount of work being done, reduce the amount of time this program runs by throwing more and more CPU cores at the problem. So if we have if a program is doing a lot of parallel computation, we can of course get a lot of speed up that way. But how much speed up, and is this an appreciable speed up for a certain amount of CPU cores? That's one of the things we'll actually be investigating. So, for the syllabus, we are going to be writing a few programs and then benchmarking how well they run. One thing to keep in mind is, like, if we have a lot of data being processed, but that data can be executed parallel, can be processed in parallel, then yeah, we might be able to get an appreciable speed up by throwing more CPU cores at the problem. But if it's but here's the other thing. If the runtime of this program is on the order of a few seconds, is the speed up from parallelizing this program worth it? So, my point is this. Here's what I'm getting at. If the runtime is like 1 second, if the runtime is 1 second and we parallelize this program, is the amount of speed up worth it? On the other hand, what if this is a program that we have to execute like multiple times a day? Then it might be possible that speed up might be worth it, so we can get as many runs on this program as we can. On the other hand, what if the runtime wasn't 1 second but 15 days? Then we want as much speed up as possible. So this is what Amdahl's law is trying to get us to think about. How much of a speed up can we theoretically get, and is it worth it? So yeah, this is a outline of what variable stands for what. So S is the proportion of serial code. No, so S is the proportion of the program that cannot be made parallel. 1 minus S is the proportion of the program that can be made parallel. X is the number of CPU cores, and Y is the speed up. So yeah, that's gonna be it for this set of slides. I might post a supplementary video talking about what we're going to be doing for our first lab. I will say right now it's a basic Hello World program using pthreads. Just something that we can write out and get done pretty quickly. So that supplementary video might be out this Monday. So just watch out for that, okay? Okay, so that's everything I wanted to talk about for this week. I'm going to leave it off to you. If you still need to set up your virtual machines, the point of setting up VirtualBox is to give you an alternative to using the lab computers in Jack Brown Hall. If you already have a Mac, you're probably okay. If your schedule is conducive so that you can just go up to the Jack Brown Hall computers, you're probably okay too. If you want to follow along at home and you're able to remote access the computers that way, you're probably good too. But if you really want to work on your own, like unimpeded, then you might want to set up a virtual. Then you want to set up a virtual machine on your own computer. That's the point of last week's discussion, setting up VirtualBox. And again, this is so that you have something that you can work on your labs more conveniently than going to the Jack Hall computers. Okay? If you have any questions about that, definitely email me about it. And yeah, that's going to be it for this week. I'm going to be posting this video as soon as possible. And we'll continue from here with the Hello World project using Ptrans. Alright? Take care.